Okay, so let's have a look at galvanic cells and electrolytic cells in comparison. First of all, galvanic cells have evolved a lot, to become the batteries that we see today. So galvanic cells, traditionally 2 beakers, and you have a piece of filter paper, salt bridge. But really, galvanic cells as, simple batteries or simple or primary cells need to be portable. So obviously you can't have them as the 2 beakers. So usually what we see is we will see it in one compartment, but you still have separation. And usually the separation of the 2 is something like a porous membrane, which only lets through certain ions, so it won't let through the reactant ions so that they can't react spontaneously together. So we still want to get that separation to get electrical energy. So galvanic cells, you have separation. Sometimes it's not even physical separation with a membrane. You'll just have one of the reactants in a paste so that you can't have like that free movement, free flowing. So separation of reactants. Whereas you have no separation here, don't have separation. Okay, in electrolytic cells. Electrolytic cells are commonly, or you don't need to. If you're talking about recharging a battery, you'll still have that separation as well because it was present originally. Electrolytic cells are commonly used to plate, so electroplating. Electrolysis is commonly used to recharge batteries. And also electrolytic cells to make or to produce metals or chemicals hard to produce through other means. Like, for example, if you want to produce pure sodium, as you can see that because sodium is so far down on the series, it's actually really hard to reduce into sodium solid. So it's very hard to produce this. So we can do that through electrolysis. Okay. Another thing that they have in common is that reduction occurs, just might actually zoom out a bit. Reduction occurs at the cathode in both cases. Galvanic cells produce electricity, an electrolytic cell requires electrical energy. So I'll just give you an example of an electrolytic cell. So for example, plating. So what we do there is we just have the one beaker We then have the object that we want to plate, like a metal spoon, so something conductive. Okay. Then we hook it up to a power supply. So that's a really telltale sign that we have an electrolytic cell. And we connect it to the metal that we want to plate with usually. So for example, let's say we want to plate with copper. And then in solution, we will have copper 2 plus. So we attach the negative terminal of the power supply to the object that we want to plate with. So it's forcing electrons onto it. At this electrode, at the cathode, we will have copper 2 plus being reduced onto the spoon. Here we have electrons being dragged up. Now the options for oxidation would be copper solid or water in this case, because they're the only two reductants present. But copper solid is stronger. So copper solid will actually be oxidized. So at the anode, we will have copper solid producing copper 2 plus 2 electrons. All right, but the anode is negative because the cathode is negative because it's actually attached to the negative terminal of the power supply, whereas the anode is positive because it's attached to the positive terminal of the power supply. In a galvanic cell, as we learnt before, there's the separation and you actually have reduction at the positive cathode. So it's still the cathode, but it is positive in galvanic cells and negative in electrolytic cells. Okay. Let's go through recharging a battery. All right. So let's just say that we do have a simple galvanic cell and we want to recharge it. And on our electrochemical series, we have A2 plus and B2 plus underneath it. And we have, I don't know, 0.4 positive and 0.2 positive. All right. So let's have a look at the two situations. So we'll call this side discharge and this side recharge. Slightly different. So we've got in solution A2 plus and as our metal A solid. And on this side we have B solid and B2 plus. Okay, so during discharge we are getting electrical energy. All right, and we've actually got no external power source there, so you've taken your iPhone off the power source, so you're actually just getting electrical energy from it, and your battery will become more and more flat over time. Here we have a salt bridge because it's a typical beaker galvanic cell, but you know, not all of them have that. You could have the membrane separating the two. Anyway, because A2 plus is the strongest oxidant present, it will be reduced. So your cathode is A solid and your anode is B solid. Your cathode is positive because we're getting electrical energy, and your anode is negative. And reduction occurs at the cathode, and it will be reduction of A2 plus 2 electrons, producing more A solid. So your A solid will increase in mass over time. All right, as oxidation, just write oxidation here, you'll have B solid producing, B2 plus 2 electrons. Okay, so that will be occurring at the anode. So your B solid will reduce in mass over time. Then we add an external power source. So if the maximum cell voltage generated during discharge is 0.4 minus 0.2 is 0.2 volts. During recharge, we need to introduce a power supply which gives us a greater potential difference. It's not equal to or greater, it has to be greater than the potential difference generated by the cell during discharge. So 0.2 volts, for example, if we're running it at 25 degrees Celsius. Okay, now we want to force the electrons to go in the other way. So during discharge, the electrons are being traveling naturally towards the A side. So we want them to actually travel towards the B side. So we'll connect the negative terminal of the battery to the B electrode. And that will force electrons to this electrode. And as a result, those electrons will be accepted by the strongest oxidant present. And because there's no A2 plus present in that half cell, you only have B2 plus, you'll actually have the reduction of B2 plus. Which is reduction. And in this case, it's at the negative cathode because it's where reduction is occurring. Okay, so now B solid is the cathode and it's negative. On the other side, you have A, and A will be connected to the positive terminal of the power supply. So it will be forced to give up electrons. And the only reductant present is A solid. We'll just assume. We're not looking at water in this case. Water can cause all kinds of complications, so unlikely to be present. All right? But yeah, we've got aqueous in this case just as an example. So we have A solid. A solid will be oxidized. Oxidation at the positive anode. So A solid produces A2 plus 2 electrons. So if you really look at these side by side, you can see some similarities and differences. First of all, the negative electrode actually remains the negative electrode. So when you are recharging a battery, it's important that you connect negative to negative and positive to positive. A difference is the anode is now the cathode, because where you had oxidation occurring, you want reduction to occur. All of the half equations are reversed, and therefore the overall equation is reversed. So the overall equation during discharge was like so. And the overall equation during recharge is the exact opposite. Okay. Another thing is that while you have during discharge, you have that spontaneous negative gradient reaction. During recharge, you have the positive non-spontaneous reaction, hence why you need to give it electrical energy to undergo that process. So I think the best thing to do right now is a few examples to just see this in practice. So what we'll do is we'll skip the fuel cells, because we'll come back to the fuel cells when we've gone through the theory. And we might just start here, electrolysis, around here. So 2.3.7 is where we'll begin. Just zoom in. All right. Faraday's laws is pretty easy, and I'll just show you where you do get those in your data book, so you don't have to memorize those equations. Electric charge. So Faraday's laws are to work out, how much metal we're going to get after a certain time, or how much product we are going to get after a certain time. So it really relates time to it. So charge equals I times T. You just need to know how to use these. So this is charge. This is current. And this is time. So we call these three the symbols. All right, Q equals I times T. The units are charge is in coulombs or C, current is in amps, and T is in time. In seconds. Now, if we broke that down, current is actually the amount of charge going through per second. So it's actually coulombs per second. So if you're doing a simple multiplication here, coulombs equals coulombs per second times by second. The seconds actually cancel out. That's why you get coulombs from this equation. The other one that you need to be aware of is Q equals NE times F, because it allows you to relate the two equations together. Basically, because we're looking at reduction, like for example, if we're looking at the amount of product obtained, metal obtained during electroplating, you have the transfer of electrons from the reductant to the oxidant. And these electrons carry a charge. What charge do they carry? Well, I think that's in your data book as well. Yes, it's here. The charge on one electron is very small, negative 1.6 times 10 to the negative 19 coulombs. We'll do a quick calculation. So 1.6 times 10 to the negative 19 coulombs is carried by one electron. I want to know how many coulombs is carried by a mole of electrons, or 6.02 times 10 to the 23 electrons. And quick calculation. Oh, yeah, calculator's here. So let's do a quick calculation. 1.6 times 10 to the negative 19 times Avogadro's number equals 96320 coulombs per mole. Well, that's also already been calculated for you in your data book. 96500 coulombs per mole. So that's the reason it's slightly different is because that's been rounded. So I would be using this. I don't know where you'd be using this. I've never seen that in an actual calculation, but you never know. So it's good to know that it's there. So Q equals NE times F. That basically what that means is if 1 mole of electrons carries a charge of 96500 coulombs, one mole of electrons carries a charge, so 96500 coulombs carried by 1 mole of electrons. We want to know how many coulombs are carried by 2 mole of electrons. So it would just be 96500 times by 2, and you get 193,000 coulombs per 2 mole of electrons. Basically, that's that equation here. So it's working out how many coulombs based on the number of mole of electrons going through. So if you put a 2, it'd be 2 times that, 96500. So here it's 96500 coulombs per mole. That's the units, times mole, number of mole, equals coulombs. So again, mole cancel out. So that's how you get number of coulombs. So if we just have like 1 Faraday going through, we are talking about 96500 coulombs of charge going through. But we're also talking about 1 mole of electrons going through. Because sometimes they talk about it in Faradays, like what they're doing here. So it says here when 0.02 Faradays of electricity are passed. So 0.02 Faradays means you have 0.02 mole of electrons. Were passed through an electrolytic cell containing chromium chloride solution. 0.35 grams of chromium was deposited. What charge is the chromium? It's a very common question. So first of all, what we'll do is we will work out the moles of chromium present. We've got to work out the charge. So we've got to work out X plus, what it is, plus X electrons produces chromium solid. Got to work out what X is. So first we'll work out the moles of chromium. Moles of chromium equals mass over molar mass, 0.35 over 52. Equals 0.0067 mole. Now, we know from the question that we have 0.02 mole of electrons. So what that means is the ratio is 0.02 to 0.0067. It's a really ugly ratio there. We have to work out the whole number mole ratio there. So what you can do is apply your knowledge from an empirical formula, divide by the smallest. So if we go 0.02 divided by 0.0067, we actually get a 1 chromium to 3 electrons mole ratio, meaning that the chromium must have been 3 plus, which means that it is actually option C. Okay, now having a look at the next question. Electrolysis was carried out using these solutions. Inert electrodes were used. It was observed that initially the negative electrode gained mass because a metal deposited on it. After some time, a gas was evolved. What are the identities of the metal? All right, this is really quite easy. I'm just trying to work out if they're in the same solution, in a mixture. Okay, so these kind of questions, you're just looking at your electrochemical series. I would basically follow these steps when you're given these questions. So determining the products of electrolysis. What I would do is 1, determine the strongest oxidant at the anode, at the cathode, and it will be reduced. Step 2, determine the strongest reductant at the anode, and it will be oxidized. So let's have a look at what we've got present according to our electrochemical series. Yeah, I'll just use this one. All right, so it says that we've got magnesium sulfate. Magnesium sulfate is Mg2+, aqueous, SO4 2- aqueous, and also you've got water because it's aqueous. And we've got nickel sulfate, so Ni2+, sulfate, don't have to write that out again. It says that we've got inert electrodes. All right, so let's have a look. You've got, I'll just use a red pen. You've got Mg2+, nickel 2+. You have water here. You've got water here. And that's it, because you don't have sulfate there. So let's have a look. At the negative electrode, this is electrolysis. So negative equals cathode. So you're going to be looking at reduction. So nickel is the strongest oxidant, so it will be reduced first, and then you'll come down and you'll get water will be reduced next to produce hydrogen gas, and then you'll actually never get magnesium depositing. To deposit magnesium, you would need liquid magnesium, some sort of ion. So let's have a look. The identity of the two are nickel and hydrogen, so giving us D. Okay, so let's give this question a go. A colourless, odourless gas is evolved at the anode when a 0.6 molar solution of potassium fluoride is electrolyzed. All right, so let's have a look at that. Potassium is here. Is here, which is much further down than water. So actually it will be water being reduced at the anode though. So let's have a look at the anode. We've got fluoride. So fluoride is actually up here. So it's much weaker than water. Water will be oxidized. So the half equation that we're interested in is the oxidation of water to produce O2 gas plus 4H plus 4 electrons. Okay, so 0.6 molar solution is electrolyzed for 5 minutes with a current of this. Determine the volume of gas. All right, so first of all, Q equals IT equals 4.5 amps times 5 minutes, but we have to put that into seconds. So 4.5 all right, equals 1350 coulombs. Then we go Q equals NEF, and we rearrange because we want to get the moles of electrons, equals Q over F equals 1350 over 96500. 0.01399. Then we use the mole ratio. We're interested in the volume of oxygen gas at SLC. So we expect less moles of the oxygen gas than moles of electrons. So moles of oxygen equals 1/4 of the moles of the electrons equals 0.0035 mole. Then we'll do volume of oxygen at SLC, and we'll use moles equals volume over molar volume, which you actually get given. If you have a look here, molar volume at SLC is 24.8 litres per mole. Also, you get the formula moles equals volume over molar volume. Yep, so volume equals moles times molar volume equals 0.0035 times 24.8. Delete that. And sig figs, 2 sig figs, 4.5 amps equals 0.087 litres. And we'll double check the answer, 87 mils, but it doesn't say that it needs to be in mils, it just says determine the volume of the gas. All right, next question. We have some nice looking questions coming up. A few pages of them. All right. So the down cell. All right. Sodium chloride is used as an important raw material, the down cell. Yep. A molten mixture of sodium chloride and calcium chloride are placed in the down cell, and a current of blah, 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 amps is applied throughout the mixture. Write a half equation which occurs at the anode. All right, this can be quite confusing, so let's have a look at our electrochemical series. All right, it says a mixture of sodium chloride and calcium chloride are placed in there, and then you just have, tells you that you got molten sodium liquid coming out. But let's use first principles. Let's have a look for the strongest oxidant present. So you have sodium present, you have calcium present. Oops, sodium present, calcium present. You don't have water because it doesn't say aqueous, it says molten. So that molten tells you that no water is present, which is good to take note of. So half equation which occurs at the anode would be the thing being oxidized. So the thing being reduced would be sodium, because sodium is in fact the strongest oxidant present. Thing being oxidized at the anode, you've got chloride present. You also don't have any water. Anything else present? No. You've got an iron mesh screen, or sorry, steel mesh, no. doesn't even tell you if there's iron. Okay. So you actually just have chloride. So the half equation, oh, I might write it out on another sheet of paper. I need 3 sheets of paper here. Yes. All right, so part 2.3.17, part AI, you will have chloride. Now make sure you've got liquid, even though it's aqueous on the series, but you don't have water present. Quite clearly says molten. Produces chlorine gas plus 2 electrons. Double I, with reference to the table of sand electrode potentials, explain why calcium metal is not produced at the negative electrode. All right, so at the negative, you've got calcium, which is further down. All right, so calcium 2+ liquid is a weaker oxidant than Na+ liquid, and therefore will not be reduced at the negative cathode. As Na+ will be reduced in preference. Okay, so it's a weaker oxidant, really need to say that, and Na+ will be reduced in preference. They're really important. Okay, calculate the length of time required for the cell to produce 100 kilos of sodium metal if the cell operates at 85% efficiency. All right, the 85% efficiency can be looked at in a number of ways. First of all, I think the most obvious way would be, all right, mass obtained divided by mass expected equals 85, well, times 100 equals 85%. The mass obtained is 100 kilos. The mass expected could be X, and you can just solve for X quickly. So, okay. Okay, so in other words, we should have gotten that many kilograms if it were 100% efficient. So we're going to have to put in more energy to put in to give us a theoretical mass of this, because we only actually get 100 kilos. Okay, so you can do it this way. So moles of sodium equals mass over molar mass equals 117.65 over 23. I'll show you 2 ways to do it. Okay, so divided by 23 equals, kilograms. So times 10 to the power of 3 grams. Make sure you're putting it into grams before you work out the moles. So do that again. Okay, divided by 23 equals 5,115 mole. Moles of electrons, well, we know it's a 1-to-1, equals that many mole. Q equals Ne times F. 5115 times 96500. Huge number. 493606138 coulombs. Q equals IT rearranged. T equals Q over I. 493606138 divided by 75000 equals 6581 seconds. Divide that by 60 equals 109.7 minutes. And actually, how many sig figs? 100 kilos. So equals 110 minutes. Now, another way you could tackle this question is by just plunging into it from the start. So moles of sodium equals mass over molar mass equals 100 times 10 to the 3 divided by 23. Equals 4348. Moles of electrons, equals 4348. Q equals Ne times F. And then, it's such a big number. And I equals divided by. So, okay, equals that many seconds. Divided by 60 equals 93 minutes. But then we know that it's not 100% efficient. So this is if it were 100% efficient and we were to get the 100 kilograms. So we need to actually put in more time by doing 100 over 85. How much more time? That's that ratio equals 110 minutes. So whichever way makes more sense to you, just do it that way. All right. Next question. Oh, B. Nelson cell. A saturated solution of sodium chloride is used. The cell employs a semi-permeable membrane which prevents the passage of chloride ions through it, but allows the passage of sodium ions. Okay, semi-permeable. So allows some ions to go through and others not to. So that means these chlorides can't pass through to that side, but notice that we do have chlorides on that side. I think that's important to note. Okay, write a half equation for the reaction occurs at the cathode. So the cathode will be the negative cathode. Okay, so let's have a look. So we're looking for the strongest, the strongest oxidant present. So you have sodium, which is present. Okay, you also have water. I think that's it. It's because it's aqueous sodium chloride, only the sodium can go through and obviously the water's going through. So water wins, so therefore part I, you have the reduction of water. That's why you're getting sodium hydroxide coming out, because you've got the sodium that goes through and you've got the hydroxide. All right. Part 2, suggest one reason why a semi-permeable membrane is employed in this cell. So let's have a real think about that. If we had chloride going through, would that do anything? So chloride comes through. If chloride comes through, it means that you wouldn't get pure sodium hydroxide solution. So the answers are, just having a look at the answers here. It allows only sodium ions to flow through it, thus preventing the contamination of the product, sodium hydroxide with chloride, which is the way I would have gone. But it separates the products of the reaction H2 gas. And that's also true. H2 gas and chlorine would react spontaneously. But why are we getting chlorine gas? So chloride produces chlorine, which is over here, being produced over here. So it's preventing, yeah, I guess it's saying, I would have focused on the chloride because it says it prevents chloride from going through, but yeah, it also prevents chlorine from going through, which would react with the hydrogen gas. I would have focused on the chloride because that's what it says in the question. But there you go, both answers. All right, let's have a look at the next one. An electrolysis experiment was conducted using this apparatus below. Crystals of scandium bromide were placed in a crucible and heated. The molten bromide was then electrolyzed using carbon electrodes. Results for the experiment are shown below. The equation occurring at one electrode may be represented as shown below. So the formula for scandium bromide is CSCBrX. We know that Br is -1. We don't know what SC is. Okay. At which electrode is the scandium produced? Okay. So what information do we have? We have electrode 1 and 2. At electrode 1, it's at the negative electrode, and this is electrolyzed. So this is electrolysis. Oops, so the negative one, we have the cathode. So we have reduction. At which electrode is the scandium produced? The scandium is being reduced. Scandium ions are being reduced. So therefore they're occurring at electrode 1. All right, because that's where reduction occurs. So let's have a look. Okay. So 1, forced reduction occurs at the cathode. So reduction at the cathode. All right, moving on to the next one, the harder ones. All right, calculate the amount in mole of electrons flowing through the cell. Let's do that. First, before we do that, Q equals I times T equals 0.5 times 1 hour and 30 minutes would be 90 minutes. And we put it into seconds by timesing it by 60. coulombs. And E equals Q over F equals 2700 over 96500. All right. Let's make sure we've got correct sig figs. Two sig figs. 0.028 mole. Okay. Now, part 2. So part 2 says calculate the amount in mole of scandium produced at the electrodes. So we'll do that through mass over molar mass, 0.42. Over the molar mass of scandium, and the molar mass of scandium is 45. Don't do scandium that often. So 0.42 over 45, 0.0093 mole. Okay, now write an expression in terms of X for the relationship between the number of mole and the number of mole of electrons flowing through the cell. So, in terms of X for the relationship between the number of mole of scandium, so N of scandium equals N of electrons if it was 1-to-1, but you're going to multiply it by scandium over the number of moles of electrons. So that's part 3. Bit pointless, could just go to part IV, find the value of X. Okay, so the value of X is the ratio is moles of electrons is equal to 0.028, and the moles of scandium is equal to 0.0093. So what's this mole ratio? Well, applying the knowledge from an empirical formula, we will divide by the smallest. So we'll divide both sides by 0.0093. Okay. So delete. Okay. Equals 3-to-1. Therefore, scandium is 3+, so it is SC. So X equals 3, so SCBr3. Okay. X equals just 3 then, not 3+. All right, let's go to the next one. An electroplating experiment. This is all calculations again. I really wanted to get to the batteries kind of ones. You can do that in your own time. Okay, 3 left. Excellent. So, half equations, rechargeable cells. These are actually quite easy. So, the rechargeable cells used to power devices. When the cell is producing electrical energy, okay, so when the cell is producing electrical energy, that means that it is, sorry, when the cell is producing electrical energy, it is the spontaneous reaction. And when it's producing electrical energy, the anode is negative. All right. Which of the following shows the correct electrode polarity and half reaction of the cathode when the cell is being recharged? So if this is when it's being discharged, when it's being recharged, we're actually looking for the opposite. And cathode is negative. And the cathode is where reduction occurs. So it's going to be the cadmium 2+ being reduced. So it's going to be either this one or this one, not B and C. And the cathode is negative, giving us D. All right, 2.4.5. Okay, so lead acid accumulator consists of a series of cells. Here are the half equations during discharge. So during recharge, you'd have the opposite. Okay, so part A, write a balanced equation for the overall cell reaction. That's pretty easy. So you're just adding the two together and there's the same number of electrons on each side. So it's just PbS plus PbO2 plus, 3 H pluses on this side and only 1 on that side. So net of 2 H plus on this side. And HSO4 minus is present on both sides, on the same side. So it's 2 HSO4 minus produces PbSO4 solid. And you've got 2 of those. And 2H2O. Okay, so that's a pretty long equation. Now, part 2, so this is I. Which reaction occurs at the anode? So the anode is where oxidation occurs. And you can quite clearly see that PbS is oxidized from 0 to +2 oxidation number. So with oxidation occurs and Pb solid is oxidized from 0 to +2 oxidation number. Therefore, reaction I. Okay. Part 3, what is the polarity, positive or negative, of the anode? So the anode during discharge is negative. Okay, then we've got part B. Explain why the lead acid accumulator is an example of a secondary cell, because it can be recharged, because the products of the reaction remain at the electrodes. Reaction remain at the electrodes. Okay, part C, what happens to the pH as the cell discharges? So as the cell discharges, you have 1 mole of H plus produced for every 3 mole of H plus consumed. Therefore, net 2 mole of H plus consumed. So H plus concentration decreases over time and pH increases over time. So make sure you're writing it in full sentences. Since H plus is being used up, the pH increases. D, write the equation for the reaction occurring at the cathode when it's recharged. So cathode is where reduction occurs, and we already said that this was recharged, so this would be oxidation during discharge, and during recharge it would be this, but going backwards. Okay, I won't write it out. E, the average lifespan of a carb battery is around 4 years. Suggest one reason why the life of the carb battery is limited. You'd say something like the PbSO4 slowly crumbles off the electrode. So you've got some examples here. So using common sense, The PB grid slowly corrodes and the recharging is incomplete due to side reactions. So you do have side reactions and precipitates forming and things like that. Okay, let's give this question a go now. All right, this is a redox flow battery. So remote areas, the simplified zinc bromine is below. The electrodes are made from inert electrically conductive material and a special membrane separates the electrode chambers. Yep, when the switch connects P to R, yep. So when the switch connects P to R, the battery produces electricity. By connecting Q to R, an external power source is used. So that's when you're recharging. Write a half equation for the reaction occurring at the cathode when the battery is discharging. So let's grab another sheet of paper and give this a go. So part A. So write the half equation for the reaction occurring at the cathode when the battery is discharging. So what have you got? You've got zinc 2+ aqueous. You've got bromide minus aqueous. You also have H2O. And let's have a look at the electrochemical series. So you have zinc 2+ aqueous. You have bromide minus aqueous. You also have bromine and zinc solid. Is it zinc solid? Yep. Okay, so the spontaneous reaction when it's discharging will be between the bromine and the zinc. So write a half equation for the reaction occurring at the cathode. The cathode is where reduction is occurring, so you'll get reduction of bromine liquid. So Br2 liquid produces, +2 electrons, produces Br minus aqueous. Okay, part B. In what way does the anode change as the battery is discharging? So the anode is where oxidation occurs, so that's when you have zinc being oxidized. So you can quite clearly see that the anode would decrease in mass. As Zn solid is oxidized. An important feature of the battery is the special membrane. What role does the membrane have in operation of the battery during discharge? I would say that it prevents bromine liquid, Br2 liquid, from moving to that's from the cathode moving to the anode to react spontaneously with Zn solid, because you still need those two things separated. It also has the ions. It allows ions to move between the cells. Half cells to balance for charge. Okay, then you've got part 2. Bromine cannot pass through the membrane. Explain the importance of this restriction when it's being recharged. So when it's being recharged, we are trying to make bromine. We therefore do not want bromine to spontaneously react with the zinc. So pretty much answered it in that section. D, zinc bromine flow battery produces a voltage of 1.67 volts. This is below predicted suggest one possible reason. So it's not at SLC. What gives us evidence that it's not at SLC? Doesn't really say, does it? The conditions differ from the standard conditions under which the electrochemical series is constructed. That's what they say. That would be okay in this context because they don't give you any extra information. But if they were to give you extra information, you would need to make sure that you use that. Like if they said, oh, it's at 200 degrees Celsius, you'd say it's at 200 degrees Celsius and not 25 degrees Celsius, according to the conditions of the electrochemical series. So this is the final question that we're going to go through. This is a simple primary cell. They give you the full equation. They then get you to write a balanced half equation for the reaction occurring at the anode. So the way you can tell what's occurring at the anode is oxidation, and you have the oxidation number going up for zinc. It goes from 0 to +2. So it actually goes Zn solid to ZnOH2. Notice that we sometimes separate the, we always separate the spectator ions, but here hydroxide is solid, so never touch the solids. They need to remain bound together. And a quick way to balance would be just to add the 2 hydroxides, because you have to balance with 2 hydroxides and 2 electrons there. Okay, if you balanced using cohes, then this is what you would get. You would get zinc solid, you would get the exact same thing, produces zinc hydroxide. You would then balance for oxygen by adding 2 H2O. You would then balance for hydrogen by adding H+. Then you would add 2 OHs to both sides. Okay, and that would be 2 H2O. They would cancel out and you would add 2 electrons and you would actually get the exact same reaction. But it's just quicker if you can just see the hydroxides. So just one possible role of the potassium hydroxide in this cell. So there are a number of roles, but maybe one would be to act as the electrolyte. And balance for charges, anions, OH minus, travel to anode, and K plus to cathode. Let's see what they said. So this is actually a VCAR question. They said KOH is the electrolyte, allows for the conduction, yep, cations to the cathode and anions to the anode. We definitely covered that. Okay, I'm going to go through a tough example of predicting the products of electrolysis. So let's say a question actually said that we electrolyzed a 1 molar solution of, let's go with copper iodide. No, let's go copper nitrate using an iron cathode and an inert anode. When they start giving you different cathodes and anodes, you've got to kind of ask yourself, why are they doing this? And it's usually because they want to trick you, basically. So they want you to think that iron could possibly react at the anode, even though you know that it's only at the cathode. So So if you have a look, let's just use common sense. Let's see what's occurring at the cathode. So at the cathode, that's where reduction is occurring, and it's electrolysis, so it's negative. So you're only looking for oxidants. So let's have a look. Copper 2+. I already would know that copper 2+ is a lot stronger as an oxidant than H2O. So you'll actually get the reduction of copper 2+ at the cathode. You'd get copper on top of the iron. So copper 2+, aqueous, plus 2 electrons, produces copper solid. Now, what would occur at the anode where it's oxidation? Well, that's where you're looking for reductants. What reductants are present? Well, nitrate's not there, so don't worry about nitrate. We've got water there. You could be fooled into thinking we have iron there, but we don't have iron at the anode. It needs to be at the anode to actually be able to react. So even though iron is a stronger reductant than water, it can't react at the cathode. It could only react if it was present at the anode. So if we did a switcheroo of the electrode polarities, for example. But anyway, so it has to be water, so it has to be this reaction. 2H2O produces oxygen gas plus 4H plus 4 electrons. Okay, and there you have it.